Okay, so while I'm trying to save up my time, while this is working, so I'm excited to be here. I basically want to teach you a little bit about formal verification. I want to make this talk technical, but it's a bit short. If you guys want to learn more, there is actually a workshop tomorrow that you learn much more about the technology. There's also a workshop next week. It's actually on Zoom, which is connected to Aave. And basically, you're going to write specification for Aave. And there is actually a reward for people who are writing specification. So please come. This is not coming yet, but it's somebody is going to come and help. So maybe while the talk is, before somebody comes, maybe I ask you a quick question. We are in the Netherlands. Who is the most famous computer scientist in the Netherlands? Who is the one who was actually the most computer science in the Netherlands? Dijkstra. Wonderful. Thank you. And what did Dijkstra invented? Many things, but one thing related to my talk. Something is important. What did Dijkstra invent? So Dijkstra invented shortest path, but Dijkstra is also the one who actually contributed invariant and the way of compiling actually invariant into code. So in fact, what's implemented in CERTORA, most of it actually goes, I think you are doing something good. So most of it actually was invented by Dijkstra. Okay, I'll be quick here. So this is the topic of the talk. By the way, all the material of the talk, if you want to take a picture, it's actually all in the website, and you can actually try these examples. It's all on the demo. You actually just click it out, and you see we prepared, not I, but Noridor prepared all these examples for you, so go and run them. CERTORA is actually now a sizable company. It has about 65 people. Amazing people, and I want to point out the three people who are here, Eyal and Michael and Alex. I want to point out that we have many, many domain experts. For us people in this domain, it's actually a challenge how to get this technology to work, and actually it's a challenge from a technology point of view and from security point of view. Our product is actually looks almost like a compiler, but it doesn't take the source code, it takes the byte code, and then you run it on the cloud, and you can see it on the demo, and it will give you, for all rules, it will give you some properties, and it will tell you which rule, whether it holds and whether it doesn't hold. Okay, maybe I just quick turn around. How many of you are coders, so I know? Can you, okay, excellent. So basically it's a tool for coder which integrate into your CI, and you can go with different kind of CI, and it will check your code. And every time you change the code, you run the tool. And we are assuming that the specification is separated from the code. So we have a separate file. There is this file called CVL, where you write the specification, and every time you change the code, assuming that you don't change the specification, it runs the code. And the tool does two things. It either gives you an error, and it gives you the test case indicated error, or it tells you that this rule is guaranteed to hold. So I asked you already the quiz. I can go on top of it. So all of these things that Dijkstra said, I think the last one is the most unfortunate in my mind, basically saying that testing is sort of no good. I think testing is wonderful. So the purpose of this talk is showing you interesting invariant, and basically showing you how the CERTORA tool is checking invariant. So here you see like some invariant that says a property, and then basically what happened when you are giving the tool actually gets two input. One of them is the code, and the other one is the invariant. And you can think about it intuitively that CERTORA is kind of a smart DIFF, if you know a tool like DIFF. It compares two files. It compares your code to the specification, okay? And it basically finds deviation between the specification and the code, and this deviation can be a rare bug. And the most useful thing that it finds these rare bugs, it finds these violations that sometimes also auditing people find. But the idea is that it can find it, and actually in our experience, we have run the tool after auditor, before auditor, and we find mind-blowing bugs with it. Okay, and this is a very exhaustive technology that checks the code. I want to point out that, of course, this is a very hard computational problem. So this means that the tool is doomed to fail in certain cases. But and of course, we tell you when the tool fails. And I can elaborate if you want. And actually, Alex will elaborate tomorrow. So the tool chain is fairly tricky. Basically, it goes, and Alex will go into details. The tool is actually first running the compiler, get the bytecode. Then there is some kind of a decompiler that goes from the bytecode to some kind of high-level representation. And there we have our secret sauce. We have a static analysis that infers properties of the code and simplifies them. So in fact, we can go from the bytecode to bytecode which is simpler. And by the way, I don't know if you noticed, we are contributing many, many bugs to the Solidity compiler, which actually was found by this technique and actually were fixed by the Solidity team. And from there on, we do what we call a compiler. We go to a formula. So you think about it, and this is actually going back to Dijkstra. You go to the fact that you convert every code and specification into a formula, and this formula defines the behavior of this code. And then we are using off-the-shelf solvers, okay? And off-the-shelf servers, they actually can give you, and these solvers are pretty good. They have been developed by my colleague for about 20, 30 years. They succeed in many cases, but some cases they fail. Okay, and this is of course open source. We are also contributing to this domain. Every time we have something for our customer, we're contributing open source to improve this code. So why now? So basically, as Rajiv pointed out, I've been in this field for many, many years, and actually this field precedes me and precedes all of us. So this field goes back to Turing. Turing is the guy who said already that formal verification is good. And like in many other fields, there was basically a golden period. So this is where Dijkstra was there, Tony Hoare, and all of these guys, Robin Milner, Patrick Rousseau invented, and all of these guys, they did all this fundamental seminal work. And this feels like, and Dijkstra said, nobody would use code unless it's formally verified. This is nonsense. It's very, very hard to get formal verification. And then what happened, basically, in the late 70s, people realized it's not really working. Okay, and the most interesting quote I know, which is actually contradicts Dijkstra, it says that formal verification is the future of computer science, always was, always will be. Okay? And the idea is people realize how hard is the problem and how naive is the method that come into play. And this is where my colleague and Mike went into the case. We have been working a lot, and many, many techniques have been developed. I pointed out here actually the work on the Microsoft device driver. You see actually a very nice quote by Bill Gates. So a lot of things actually have been developing. But the killer thing that happened, and this is what makes people like me interested, is this idea of smart contract. The idea is that you have code is law. So if you have code is law, if you have wrong code, you have wrong law. So in this case, you really want to develop everything, to deploy everything that you want. And basically, we are deploying all these complex techniques. And we want to do it instead of, in addition to auditing, basically to do this kind of things. So what is CERTORA goal? CERTORA is developing tools. I'm showing you formal verification, which is in the demo, but we have other tools which are coming. We have mutation testing for spec. We are checking the spec because we have found that we have bugs in the spec. We have actually fuzzing for the spec. We have many things for the tool that are coming, and watch out, actually, they're all coming. But the thing that really CERTORA wants to do, CERTORA actually wants to create a marketplace for specification. CERTORA wants people to community, and that's what we are starting now with Aave and Compound and other teams. We want actually people to contribute rules. We want people to help us in writing specification. Also, we have collaboration with auditors. The idea is the auditors will provide specification, and then we use our tooling to check the properties. So this is a very, very simple example how this tool is working. You take this tool. There is a very, very simple environment that you say that the sum is equal to the total, and the tool is able to check it. Just to show you, this is a very, very simple bug that will be identified by the tool. You see, actually, you get this thing, and then it will tell you that if you are moving something to yourself, you are breaking the rule. This is a very, very simple bug. You can find it by many other techniques. I'm going to show you much more interesting bugs, and if you run the tool, you can show much more interesting bugs. But the idea is by comparing the code to the specification, we are finding many interesting bugs. So how is this going to work? Wow, 8 minutes. Okay, I'm not going to speed more. Okay, but so how is this going to work? So I'm sorry, I'm explaining it in a more high level, but maybe you can get the low level later. So the idea is you start with the design of the code, and then what we advocate is that when you're writing the code, you write the specification. We have our own language, CVL, and we advocate that you write the specification early, okay? Because this specification will give you something. And then we do testing, like the normal testing, and then we do mutation testing for the spec, and then we do fuzzing for the spec. Then we do auditing. What is auditing? Auditing is a very useful procedure that you ask somebody from outside to check the code and to check the specification too. And we have actually teams who are reviewing, in addition to the Solidity code, they are reviewing the specification. And then we applied our technology. We apply this formal verification, and at the end you get a proof that the code is correct. So this is the procedure that we advocate, and of course there are other procedures that you can do, but this is what we advocate. So just to give you very, very quick a summary, this is a very interesting use case. It's actually a customer of us called DeFi. Maybe they are here. Are they here? No. So basically, they are using the tool on their own. And what they have done, they use the tool and they compare it to auditing, they compare it to other approaches. And you can see that that's a blog that they wrote. In fact, what they see is that the tool actually is finding many more bugs than others. And they wrote a specification. In terms of us, we have actually have been running this tool extensively on the cloud. You see the numbers. We are actually protecting significant amount of money. Of course, it's not mean that it's fully verified, but it means that we have actually increased the confidence on this code. We are running significant number of Solidity lines, or actually we are running on the EVM, but we count the Solidity line. And maybe this is the thing that we are the most proud of. We have found a lot of bugs and we prevented them before the code was deployed. And these are substantial bugs. For example, a solvency bug. A solvency bug means that you deposit money and this money is gone, okay? And I'm sure if I have time, I'll show you several of them. But this is the idea. We are finding these bugs before the code is deployed. We also found some bugs after the code is deployed, and we're of course more quiet about it. These are just quotes from customers working with us, and we love this domain because I think people engage with it. So I mentioned specifically the Compound team, which actually worked with us after they completed an auditing and the tool found bugs, but all other fantastic teams, I won't be able to go over it. I have 5 minutes. I have 5 minutes. So I want to give you just the glimpse of it, and I'm going to show you some kind of a code. I'm getting here a little bit more technical, but this is basically a simplified version of the SUSHI pool or Trident. So it's implement basically a product pool. You have your product of 2 tokens, and for example, here you are buying 50 tokens. So what you see is you're buying 50 tokens, and in addition, you see that it changed the token B and token A, and because the multiplication is almost constant, then you see that you give back the number. And you can also do some other operations which are slightly more tricky. For example, you want to actually invest token. So this changed the number. So here you see that it changed the liquidity pool. It's because the ratio is 1 to 2, so it's add 20 to the liquidity pool. And you see this changed the product. But still the ratio actually remains constant. And you can actually, this is actually another operation which is very interesting. You do this burn single. So what does burn single do? You basically get rid of one of the token. Okay, and actually many of the protocols support that. So you see this burn single, and the question is what properties you have. So you have 2 properties that you made, that basically the square of the LP token is equal to the token multiplied by the token. And the other one is that the LP token is greater than 0 if and only if the token is 0. And this is the code. It's getting very technical. I'm not going to go it, but the idea is we can write it in our CVL code. It looks like Solidity. It's not exactly Solidity. You have to think in different ways because you are starting an arbitrary state, but I won't be able to go and explain to you. Instead, and here you see that in fact, this is a bug that it prevented. It prevented a bug in which you can actually change money to somebody else. And this is a property, by the way, that you can write to many protocols. I don't want Rajiv to reduce my income, okay? So I don't want, I hope, okay? So this is the idea. I want to show you this one bug here, which is so simple and so beautiful. I have this minute. So this is a very, very simple environment, actually, like a very, very simple environment, and you can think about it from economic perspective. What it says is that the total supply is equal to 0. So basically it says that either both tokens are 0 or none of them is 0. And that's a simple property that is CAB. And we run it on the Trident protocol before it was deployed. I want to make you sure. So, and it was audited by a very good guy. And we have 2 minutes. I will be able to show it in 2 minutes. So we ran it on the protocol and we check. Basically the tool analyzed the bytecode and it checks and it compared the code to this property. And guess what? This is what happened. There is actually a bug because the way the code, there is a logical mistake in the code and people make mistakes. And the idea is the code is not computing the reserve in the correct way. So what is the consequence of it? The consequence of it is that you break the invariant. But the fact that you are breaking the invariant, you can completely deplete the contract. Okay? So let's see how this is done. So you start by a big liquidity, and you start by some amount of token A and token B, and you are doing an operation like external transfer. External transfer, what it does, is increase your token A. So you get more of the token A, you increase your token B. Now, because burn is written in a way, most of the time burn is working. But when you have a burn, and we are looking for rare errors, that's the beauty of this technique. We are looking for rare errors, and the idea is with this rare error, now you can do burn single. And burn single, you see what happened, because you have too many token A, you can break the invariant now. You can break the invariant now, so now, an invariant, you can think about it like essential properties of your program. So once you break it, you have token B being 0. Once token B is 0, what you can do now, you can do a swap, and all the money is gone. So we don't want it. We want to write this invariant early and use techniques like us to check the code every time. And if the invariant are failed, it means something is wrong. So I don't want to go into that. I want to just basically wrap by several things, which is experience not of me. I have finished. Okay, I just put it down and I finish.